All right, welcome everyone back to CS264A, Automated Reasoning, and this is our lecture 5. Today we will finish our discussion of satisfiability, which is pretty much everything we want to say about your chapter 3. There is a whole bunch of topics that we need to finish there, including, for example, how to certify unsatisfiability when a modern SAT solver say that the knowledge base is unsatisfiable, and how can we actually prove that? And other topics like variable ordering and phase selection and so on. We'll also talk about how to solve satisfiability using local search methods, which tend to be more efficient, but come with certain caveats. And in fact, I'm going to start by talking about something known as Exhaustive DPLL, which is used for purposes beyond satisfiability, including model counting. This is actually in your chapter 4, but I will start with that because you need it for your homework. All right, so let's get started, and I will turn my camera off and head to the whiteboard next. All right, so as I mentioned, we will get started with what's known as Exhaustive DPLL. And you'll see what this does is effectively run DPLL, but to exhaustion. So DPLL typically is trying to find a satisfying assignment. So the minute it does, it stops. But what we're going to be seeing here is a little bit different. So let's start with a concrete example first, and then we will see what's going on. So here I do have a simple knowledge base, delta, which only has 2 clauses in it, not A, B, and not B, C. And we'll try to run what we will call exhaustive DPLL on that. We will use the variable ordering A, B, C. So if we look at our termination tree, it's going to look like this. So if I start with A, and then I go ahead and set A to true, remember what we typically do in this case. We will go ahead and condition the knowledge base on A being true, and then we will run unit resolution. And if you remember the function that we defined last time, unit resolution, what this will do is return 2 things. Would return a set of literals and a modified knowledge base. And if you recall what the set of literals I were, these were basically unit clauses that were originally in delta, or those that were derived by unit resolution. Those are the literals, and then we condition delta on those and we get gamma. If you do it in this particular case, that is, if you take delta and condition it on A, you will and run unit resolution, you'll be able to infer that both B is true and C is true, right? So because the literal A resolves with this, so that gives you B. And then if you take B and resolve it with this, you get it with C. So what we've been doing is writing here B equals true and C equals true. And then when you condition this knowledge base on these guys, in this case, we're going to get true. So if we were doing DPLL, we would be done at this point, right? Because this is true, and I've already satisfied the formula. And I would have returned the variable setting A equals true, B equals true, and C equals true. Now, exhaustive DPLL will keep going, all right? And you'll see in a little bit why. So I'm going to go ahead and now try A equals false. And what that means, I'm going to condition this knowledge base on A equals false. If I do that, what should why should I get in this particular case? If I condition the knowledge base on A false or the literal not A, can someone tell me what is the knowledge base that I'm going to get here in that particular case? Can someone type to the chat box? Okay, so people are typing not B, C. Because this clause will basically be subsumed, and I'm left with that. So now I keep going, and let's pick up B, and then I'm going to try B equals true. And you can see what happens here. If I condition on B equals true, then I will conclude that C is true. And at this point, I have a setting for every variable A, B, C. If I condition this knowledge base on that, again, I'm going to get through here. So that's yet another satisfying assignment for this particular knowledge base, and that is A false, B true, and C true. But once more, if this was DPLL, we would have stopped here, but we're going to keep going, and then we're going to try B equals false. So what happens in this case? I do have A false and B false. If I condition my knowledge base on that, and run unit resolution, basically, the minute I condition on A false and B false, the whole knowledge base gets reduced to true, and there is nothing that can be inferred there using unit resolution. So what you see here is this is the termination tree for exhaustive DPLL in this particular case. Let's call this the termination tree. As you can see, if this was DPLL, I would not have gone this far, but I did run DPLL, as people say, to exhaustion. And this is the termination tree that I have. And now the question is, why did I do that? How can I use this? How could this have been useful? Anybody want to make any suggestion on why would I want to do this, or how I can use this algorithm, which will show you the code for in just a second. Okay, a number of people are saying we use this to count models. Yes, and in fact, what we're looking here is kind of similar to what we've seen earlier and called a decision tree. It is almost. So if we look here, how can we count models? And again, we'll show you the code in just a little bit. But if we go down this path, this is when we set A to true, and we end up concluding B true and C true. So if I'm going to put here, a number, what should I put here as the number of models that I got under this case? Okay, I'm getting the number 4. Now, this would have been correct if I'm saying under A true, then every other possible values of B and C would be a model, but that's not the case actually. When I set A to true, I must have B true and C true in order to code a model. Okay, and now a bunch of people are saying 1. That is correct. So this would be 1 here. We got to be careful about these guys. And let me see, if we go down here, what should I put here as far as a number? Remember, what happened here is I set A to false, I set B to true, and then I concluded that C must be true in that case. So what should I put here? And people are saying 1 again here, correct. Now let's look at the very last branch here, A false, B false. The minute I did A false and B false, what happened? The formula was satisfied. Excellent. So people here are saying we should put 2 because C is free. C could be anything and I'm fine. As long as A is false and B is false, then basically I'm satisfying the formula. C could be anything. And this model, and these two are all distinct because as we've seen before, anytime I go down a different branch, I'm setting the value of some variable differently. So if we want to really enumerate these, this would be A, B, C, and this would be not A, B, and C. And here I would have not A, not B, and C, and not A, not B, and not C. So these are my 4 models. And great, you can see how I can use this to count models. In fact, we can use it to do more things. And we will see this later in the once we finish SAT and get into what we call knowledge compilation, which is the second foundational part of this course, we will see how this algorithm and variation on it can be used to do what we call knowledge compilation. But let me just do one more thing, and I will show you the code after that. And let me see here. So if we go ahead, and again, before I show you the code, I just want you to see something. If you look at DPLL, and see what is it based on, it's based on the following, that a knowledge base is satisfiable if and only if delta given P is satisfiable or delta given not P is satisfiable. Now you can pick up any variable P and do that. That is, if I want to see if delta is satisfiable, pick any variable, set it to true, and see if that is satisfiable. If it is, then you're good, and you say the knowledge base is satisfiable. If not, go ahead and try setting it to not P. And if it is satisfiable, then again, you're good. If neither of these are satisfiable, you know for sure that this guy cannot be satisfiable. And the point here is, I don't necessarily need to run these two guys. So if I start first here, and that is satisfiable, I'm done. I don't have to run the other branch. I would try the other branch only if this guy failed, okay? This is the thing. Now, if you look at, in the Zulu code I'm gonna show you is gonna call this CDPLL or DPLL for counting. If you see what's going on here, it's gonna be like this. You're gonna say, I want to count the models of delta, and I'm gonna leave room here and you'll see why. Then what I wanna do is count those models in which P is true, and then I'm gonna count those models in which P is false. And then what do I do to these guys? I'm gonna get a count while setting P to true and count while setting P to false, and people are saying we'll have to add them. Excellent. Now you can see what's going on here. The two branches are not optional. I do have to do both branches. I have to count under P and I have to count under not P. And that's why this notion of exhaustion, right? This is where exhaustive comes in, that I have to try both of these guys. Now, why did I leave this extra argument here? And this is a subtlety. We need to explain it first before we show you the Zulu code, and then you'll see why the Zulu code is written the way it's written. The subtlety is, what am I counting over? So if I come and tell you, you know, here's A or B, and I say, how many models does this have? What would you say? How many models does this clause have? Can someone type a number? Okay, so a bunch of people are actually writing 3, because if you look at A, B, and there are all 4 combination of these guys, true, 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 false, false, true, false, false, right? And except for the last one, each one of these guys will be a model. I can satisfy it using any of these 3. This would not be a model. Okay, well, here's the tricky part. You assumed here tacitly that we are counting over 2 variables A and B. It is possible that the knowledge base in general is over 3 variables, A, B, and C, but it happens in this particular state that it is reduced to A or B. If indeed I was counting over the variables A, B, C, then 3 would be the wrong count, correct? If I was counting over the variables A, B, C, what should be the count in that case? And people are saying 6. A whole bunch of people are saying 6. That's 3 times 2, because C could be either true or false. Okay, and that's why in general, when I want to count, I want to tell you how many variables I'm counting over. And in this case, I'm counting delta over n variables, and when I go ahead and set one of them, then this should be -1 and this should be -1. This becomes particularly important. For example, one of the cases where it comes up is if your knowledge base reduces to true. And maybe after setting, let's say I have 10 variables, and the minute you pick one of them P and condition on P true, maybe the knowledge base reduces to true. In that case, what is the number of models for true? Well, you have to tell me over how many variables are you counting. In this case, I'm counting over 9 of them. So it would be 2 to the 9, all right? And if this instead was 5, and you went ahead and conditioned on P equals true, and then the whole knowledge base reduced to true, then I'm counting now over 4, and then it would be 2 to the 4. Okay, you see now why we need to keep track of how many variables we're counting over. Okay, so we're ready to go ahead and show you what the Zulu code looks like in this case, and you'll see it's very familiar given what we've seen before, except for this little thing about keeping track of the variables that we have to count. So give me a second here while I go ahead and upload the code for you so you can see what's going on. All right, so this is the algorithm we just illustrated by an example. We're calling it counting DPLL, and it takes a clausal form and the number of variables and returns the number of models. So we've seen all of this before. Here's the two base cases. In the base case where this is true, we basically return 2 to the n, right? N is the number of variables we're counting over. The other base case, if it's inconsistent, the empty clause appears there, then we return a model count of 0. And this is where we've seen last time where we're choosing literal to split on. We've seen these two cases before where I'm basically trying L and then counting, doing unit resolution. And then in this case, I'm setting not L and doing unit resolution. We know what these guys are. And finally, here are the two recursive calls, right? So I'm counting this and I'm counting that. And what you can see here is this is the number of variables that have been already set. I want to remove them from N. And this is the number of variables that have been set in this case. I'm going to remove them from N. So what we did here on this side is effectively applying this algorithm, which once more is referred to as exhaustive DPLL. So this was actually the first algorithm, I believe, that was proposed for counting models. Since then, people have made many more improvements on it. Which makes sense when you are doing exhaustive search, if you want to call it that way. We will come back to this later because we just gave you the basics here, because as I said, it ends up playing a role bigger than simply counting models. It can be used to compile formulas. And I will leave you here with one exercise if you want to try at home, which is, we talked earlier about the notion of a decision tree as a way of characterizing the models of Boolean formula. And we did that discussion in the context of directed resolution and how directed resolution actually can aid us in constructing a decision tree. What we did here is very similar to that algorithm. The two differences are this decision tree was not exactly what we did before. We didn't have that thing before. So you can actually go ahead and unfold this a little bit, knowing this, and make this look like the decision trees we looked at before. Otherwise, this is pretty much the same algorithm. The other difference is in this particular case, we are running unit resolution in the background. In the previous case, we were taking advantage of the work that directed resolution did. So when you read this section in your in your chapter 4, go back to the section on constructing decision trees using directed resolution and try to compare the two. You'll find that quite informative. Okay, this is as much as I want to say about this particular topic here, and I'm gonna go ahead and move to something else next. And let me erase this. All right, very good. The next topic that we want to discuss, it's in general, we can refer to it as certifying UNSAT. But in the context of doing this, we'll actually end up looking at a technique that is relevant to what we did last time, which is how do we generate these asserting clauses. In fact, there was a question about this, like how can we do it efficiently? We looked at the notion of an implication graph and how we can look at various cuts in the implication graph, and some of them correspond to asserting clauses. And then we made another further distinction where we talked about first-UIP asserting clauses, and there was a question of how can we do that efficiently. And it turns out there is actually a very nice way to do that. And what we'll start with is that simple method for generating these asserting clauses. And the reason is that beyond showing you how you would get to implement this, we will see that that also serves the purpose of certifying UNSAT. So what is certifying UNSAT? So you run a modern SAT solvers and two things can happen. It can say that the knowledge base is satisfiable, And these algorithms will give you back a satisfying assignment. It's pretty easy to check if an assignment that was returned is satisfying. Okay, we've seen that. You can take the knowledge base, set those variables, and see if the formula got satisfied. But what if you get back an answer of saying that the formula is unsatisfiable? And people are interested, how can I verify that? How can I verify easily that indeed the knowledge base is unsatisfiable? So people talk about a certificate. I give you back something that is kind of a proof or certificate of unsatisfiability. And now we'll see how this works. But again, we will first start by talking about a simple method for generating asserting clauses, and then you'll see the relevance of that to certifying UNSAT. We will talk about two different methods for certifying UNSAT. The first is based on what we're gonna be doing next. So what I will be doing now is first I will write the codes for generating these asserting clauses, and then I'll put up an example where we trace it, and then you will see two things again: how it's a nice way of generating asserting clauses and how it can be used to certifying UNSAT. So let me go ahead and write the code here. It's relatively short and it has a number of steps. Let me go ahead and write it all and then we will go over it. All right, so what we have here is the procedure. I'll read it, and there is a couple of terms that will become clear once we do the example. So I'm going to start by setting the learned clause to the clause that became empty during unit resolution. We do invoke this procedure when we hit a contradiction using unit resolution. And we know that that happens when one of the clauses becomes empty. So that clause that became empty, we start with it. And then we just repeat this loop. As long as this learned clause is not asserting, then we go ahead and do two things. We look up the literal in that clause that was falsified last, and then we update the learned clause to be the resolvent of the current learned clause and the reason of not L. This is not clear yet. We'll see what that means in just a second. We just keep repeating this until the learned clause becomes asserting and we go ahead and return it. And we're going to see this in the works by tracing this particular example. So what we will do here is we will look at three things that we've seen before. Let me put these in red here. And so I'm going to have the decision level, and then I'm going to have the assignment that we have. And then here I'm going to put the reason, which we didn't mention it before. But basically the reason is when you infer a particular literal using unit resolution, when you infer that A must be true or A must be false, you do that based on a particular clause. And that clause is called the reason for that assignment. So let's do that here and see what happens. In this particular example, let's go ahead and say that we start and we made the first decision, which is A. So this is, okay, we know that we have the first level, which is -1, and this is nothing. And then we level 0. Let's say we go ahead and make the decision A. Now, if you do that, basically nothing happens in this particular case. So unit resolution does not discover a contradiction. So we go to the next level 1, and let's say we set the variable B to true. So this is our second decision. So we first made a decision A and then decision B. Now, at that particular case, unit resolution will start inferring things, and it will infer that C is true. And the reason it does that is because of this particular clause, not A or not B or C. This particular clause is one of these guys. Actually, it's the very first one. And remember, because I had A true and B true, resolve, you actually conclude C. So this is what's called the reason for that guy. And then further, it will go ahead and infer. Anybody can tell me what else I can infer in this case? Maybe D. Someone is saying D. And the reason for D is basically here, right? So because I have B true and C true, these guys get resolved, so I get D. And this is here the reason for that inference, not B or not C or D. Okay, so these are these particular guys. And remember, B, the decision was made at level 1, so these inferences are both at level 1. Now, at this particular case, well, we get the clause not C or not D to become empty. And therefore, I have a contradiction, and people are saying I could have done a contradiction in a different way, but let's go with the sequence here. So what we get is that this guy becomes empty, and therefore we have a conflict. All right, so let's trace this procedure now. So now I want to find an asserting clause, and according to this procedure, I'm going to go ahead and start by not C or not D as my learned clause. Now, the second part says, while the learned clause is not asserting. Is this asserting? Is this asserting in this case? Remember, what are the levels here? This was done at level 1, level 1. Asserting clause should have one literal or variable setting that was inferred at the last level. So it's actually not asserting. So if I want to look at this, and it will say, okay, identify the literal in the clause that was falsified last. Which one was falsified last? This guy, because I had D was derived the last guy, and this was falsified last. So this is L in this particular case that I'm looking at. And then it says, okay, now update the learned clause. We started with this, now we're going to have a new one. What is the new one? Resolvent of the learned clause, this guy, with the reason of not L. So if L is not D, not L is D, and I want to resolve this with the reason for D. This is the reason for D. So if I resolve this guy with that guy, what do I get? What do I get in this particular case? If I resolve this with that, so I'm resolving over D. I have not D here, and I have D. What should I get? B, not B, or not C. Okay, not B or not C. Now, the question again, is this asserting? Is this asserting? Now, B was derived at level 1 and this also at level 1. So it is still not asserting, right? So now I have to continue, and then I have to pick which one of these was falsified last. That would be C, because look at the order here. So again, this is the guy that I'm going to call L. So what should I do according to this procedure? I should go ahead and resolve this clause with the reason for C. This is C. This is its reason. So I have to resolve this with that. And what happens in this case? What do I get as a result of that? What do I get as a result of that? Can someone type what's the result of resolving this with that over C? And people are writing basically not A or not B. Now, is this asserting now? Is this asserting? Yes, it is asserting. Excellent, because this guy here was done at level 1. This was at level 0. There is one literal only that is at the last level. So I'm basically done. And that would be my asserting clause that I learned. And the assertion level here is 0. So if I were to continue with the algorithm, then I will go ahead and erase these guys. I would erase these, right? And let's remove this guy as well and go back to this level where I only have these two decisions. And then I would go ahead and add that particular clause to the knowledge base and then run unit resolution and so on. And if I actually do that, I will end up immediately inferring B, and the reason for B would be this guy, which I just learned, and the process goes on. Actually, I will have not B. I will have inferred not B at level 0. Now, the example in your chapter keeps going, right? And you will see that, okay, now I can go to level 1 and do other things. But I'm gonna try to get to the chase here and tell you what else is this useful for, which is certifying UNSAT. And you can see the rest of the details in your text. But just before I do that, you probably have realized that when doing unit resolution, we would have choices. And I picked some of them arbitrarily, right? So in getting a contradiction using unit resolution, you could have done it in multiple ways. And that would have changed things. And I just did them one way. So some of you have asked, why didn't you resolve this with that? You know, we may have had some choices there. And one of the questions I'm having is why did we choose this as the initial learned clause to start with? Because we basically start with the clause that became empty, that reduced to the empty clause. And in our example and the sequence of way we did this, that was the clause that became empty and triggered a contradiction. It's possible that you could have done unit resolution differently and something else became an empty clause, then you start with that. Okay, now let me tell you what happened here. I'm gonna erase this part, and you can see that what we did is a little bit more than simply get a learned clause. The way we did it, we also got a proof or a resolution derivation for that particular clause. So what happened here, okay, I did now erase the details, but you remember them. What happened is, this is the guy that became empty. Actually, let me do it in red. This is the guy that became empty. And then the one we started with as the learned clause. And then because it was not asserting, we went ahead and resolved it with this guy. And when we resolve them, we get the second candidate for the learned clause. And we were still not happy with that because it was not asserting. So we, following the procedure, we went ahead and resolved that with this particular guy. And then we finally got what we want, which is this guy, which in this case was asserting, and therefore we stopped and we said, good, we want to learn this guy, okay? Now, what happened here? Not only did I give you an asserting clause, but I justified it. Because remember, what we had from before is that these learned clauses are implied by the knowledge base, right? And if someone, you know, if you learn a guy and someone comes and says, well, how do we know that it's really implied by the knowledge base, what you've added there? Well, here's the proof. And so you do have a resolution proof in this particular case. Now, if you were to finish the example as we did it, we stopped somewhere in the middle. But this example that you have here is actually, the knowledge base is inconsistent. So if you were to keep going with it, you will eventually end up returning UNSAT. What will happen in that example, and you'll see the details in the chapters, it will keep going, and then it will end up inferring X, and then it will end up inferring not X, and therefore you get a contradiction. But because these clauses were all generated in this fashion and they have the proofs, you will see in your text a full resolution proof on how we were deriving things, and then we ended up, you know, deriving X, and then another part of the proof that is, you know, end up arriving not X, and this gives you the empty clause, right? So because of this procedure and the proofs it generates, you can get at the end resolution proof of the inconsistency, and this would be your certificate. So you can give someone back this resolution proof, and this is my certificate of why this knowledge base is unsatisfiable. Go check it. Okay, checking a resolution proof is easy, right? Every resolution step is easy to check. So you can then verify for yourself whether that knowledge base is indeed inconsistent or not. Okay, so this procedure was quite valuable. It played these two purposes, but I'd like to end before we go to our break with a question to you about how else could we have verified or certified unsatisfiability without necessarily using this much space, okay? Because here I'm giving you basically a whole proof. So I'm going to pose a question for you. Here on this side, I have a modern SAT solver, and this is you, the user. Now, this guy may come back, and as we said, with you give it a knowledge base, and it can go back and give you a satisfying assignment, which the code we wrote didn't do that, but you can make it do that easily. Or it could say unsat, right? Okay, we know that this is easy to check. Now the question is this: you as a user, you get the unsat answer, and you don't just blindly trust the modern SAT solver. You want to check for yourself that it is indeed. And then you're going to ask this guy, can you give me some information, some certificate so I can check? Now, we're going to assume that this user has access to a box that can run unit resolution, only unit resolution, not general resolution. Okay? Having access to a box that run resolution, that box is complicated because there's so, it's hard to do general resolution and there's so many choices. Unit resolution is something much simpler. We can run it in linear time, and that's the only thing you have access to. So you can go ahead and run a box that does unit resolution, and you want this guy, beyond just saying unsat, you want it to give you something else so that by only making calls to a unit resolution box, you can verify the answer. All right? So the question is, what should that be? Remember, what happens on this side is you have the knowledge base, the original one, and when this guy is doing its work, it starts adding these learned clauses. Let's call them alpha 1, alpha 2, alpha n. And remember that when it eventually concludes that the knowledge base is unsat, that happens when unit resolution generates a contradiction on these two guys without making any assumptions, where the decision sequence is empty. So when this guy finished with an unsat, it is because delta and gamma together led to a contradiction using unit resolution. So here's the question. You have access to a unit resolution box, and what do you want? What would it take for you to be able to verify the unsat answer by only making calls to a unit resolution box? What do you guys think? And as I'm waiting here, someone is saying, will there always exist an asserting clause? Yes. Okay, someone is saying, this guy will want to know gamma. Why? How can you use it? Let's say I'm going to give you gamma. So of course, both of them had access originally to delta. And then you're saying the user, when this guy says unsat, you're going to say, okay, give me your gamma because I'm going to use it. So the answer I'm getting is you need this because if this guy has access to a unit resolution box, then it will go ahead and say, okay, let me check delta union gamma. Will it produce inconsistency using unit resolution, right? That's the motivation here. And if this guy was right, then I should get an inconsistency using unit resolution. I'm done, right? Okay, not really. This is all. This is half the story. Why is this not good enough? This is on the right track. Why is this not good enough? So the guy gave you gamma, you took gamma, added it to delta, you ran unit resolution, and you got a contradiction. Why shouldn't you not be satisfied yet? There's a gap here. Excellent. Someone is saying we need proof of gamma. How can I verify that gamma is implied by delta, right? I mean, for this to be a certificate, gamma has to be implied by delta because I could have made up some gamma for you that doesn't follow from delta, and you add it. Then what is missing here is I want to verify this, that indeed it does follow from delta. Then if I can do that as first step, and then this would be fine as a second step. And I'm seeing also more people saying this. Okay, here's the thing. We'll now figure it out, and maybe you can figure it out for me, and then we will end it here as far as the first segment of today. Look, gamma is this bunch of clauses, alpha 1, alpha 2. Okay, not only do I want gamma, but I want it ordered in the same way that the clauses were actually generated. If you remember, not only, let's pick the first one, not only does the first learned clause follow from delta. If you remember how we got it through a cut in the implication graph. What that means is if I take, now I know from the refutation theorem that since this guy follow from that, then it must be that this is unsat, right? We know that. But if you look carefully about how we generated these guys, not only is this unsat, by construction of this, this unsat can be detected by unit resolution, which is not always the case. Because given how we generated these learned clauses, I'm guaranteed if I take alpha 1 and negate it and add it to the knowledge base, I'm guaranteed to get a contradiction using unit resolution, because the implication graph was based on unit resolution and this guy was based on a cut on the implication graph. So what's going on here is I can verify gamma like this. To verify the first guy, so I want you to give me gamma in this order as you derive them. I can take alpha 1 and negate it and add it to delta and then run it to resolution. I should get an inconsistency. Okay, now to verify the second one, I have to take delta and alpha 1 and then add the negation of delta 2 to that and then run it to resolution, and I should get an inconsistency. And then to verify the third one, alpha 3, I take delta, alpha 1, alpha 2 as my new knowledge base, and then I negate alpha 3 and I run unit resolution, and I should be able to get an inconsistency. And that's how you would verify this guy. Okay, so I need gamma and I need it in order, and I can verify it clause by clause using unit resolution. At the very end, when I put them all together, I should get an inconsistency, and that would be certificate. All right, folks, we're already a few minutes past our time, so let's take our break and come back at 11. Thank you.